Finally, let's look at some aspects of the threading support in Linux as well. Note that the current threading support in Linux has a lot of lessons learned based in large part on earlier experiences with threads, such as the experiences that are presented in the two Solaris papers we described. Like all operating systems, Linux has an abstraction to represent processes. However, the main abstraction that it uses to represent an execution context is called a task, and it's represented via corresponding task structure. A task is essentially the execution context of a kernel-level thread. A single-threaded process will have one task, and a multi-threaded process will have many tasks, one per thread. Some of the key elements in a task structure are shown here. Each task is identified by a task identifier. However, for historic reasons, we call this a PID, like a process ID. It's a little bit misleading. What this means is that if we have a single-threaded process that has one task, then basically the task ID and the process ID are the same. If we have a multi-threaded process, that will have multiple tasks. Each will be identified by its own identifier for the task, and that will be held in the process ID. Now, the process as a whole, basically the entire group of tasks, will be identified by the process ID of the very first task that was created when the process was first created. This information is also stored in the task group ID field. In addition, a task structure maintains a list of tasks, so this basically links all of the tasks that are part of a single process, so all of the threads of the process. And so one can figure out what the process ID for a group of tasks is also by walking through this list. Having learned from implementation efforts like the Solaris threads implementation, Linux never had one contiguous process control block like what we described at the start of this course. Instead, the process state was always represented through a collection of references to data structures like the memory management, the file management. These are all referenced via pointers. So this makes it easy for tasks in a single process to share some portions of the address space like the virtual address mappings or files. And in that case, these pointers would simply point to the same memory management structure or file structure. There are a number of other fields in the task structure. It's a data structure that's approximately 1.7 kilobytes large, so there's quite a lot of information in it. To create a new task, Linux supports an operation clone, and this is similar to this. It takes a function pointer and arguments, similarly like what we saw when we were creating a new thread, but it also has this one argument that's called sharing flags. The flags parameter is a bitmap that specifies which portion of the state of a task will be shared between the parent and the child task. As you can see, the values of these flags can have different effects when they're set versus when they're cleared. For instance, when all of the flag bits are set, then we're really creating a new thread that shares everything, the entire address space and everything else with the parent thread. They're part of the same address space. If all of the sharing flags are cleared, then we're really not sharing anything between the child and the parent, and this is more similar to what we saw happens when we're forking a new process. And in some cases, various combinations make sense. For instance, you may want to share the files or something else between the parent task and the child task. Speaking of fork, you should note a couple of things. First of all, fork in Linux is internally implemented via clone by basically having these flags cleared. And also, fork has a very different semantics in Linux and POSIX-compliant OSs in general for multi-threaded processes versus for a single-threaded process. So for a single-threaded process, when we're forking, we're really expecting that the child process will be a full replica of the parent process, whereas with multi-threaded processes, the child will be a single-threaded process. So we're really going to create a replica of the portion of the address space that's visible from the parent thread, from the parent task in the process that's called the fork. This has a lot of implications on some issues related to synchronization, to what happens with mutexes, and it's beyond the scope of the class, but I should just make sure that you're aware of this, so that's why I'm bringing it up at this point. The current implementation of Linux threads is called a Native POSIX Threads Library, NPTL. And this is a one-to-one model where there is a kernel-level task for each user-level thread. This implementation replaced an earlier implementation, Linux threads, which was more similar to the many-to-many model that was described in the Solaris papers, and it suffered from the same kind of complexity regarding signal management, etc. In NPTL, because of the one-to-one model, the kernel sees every user-level thread. It sees all of its information, whether it's blocked on synchronization, what is its signal mask, everything. This is made possible for two reasons. First, the kernel traps have become much cheaper, so the user-to-kernel level crossing that we've been trying to avoid in part with this many-to-many model has become much faster, and so we can afford to go to the kernel and update the kernel level signal mask. Also, modern platforms have more memory, so there really isn't some constraint to keep the number of kernel level threads as small as possible. So we can create as many kernel level threads as the process needs. There aren't restrictions on the range of IDs that are too stressing for most of the common processes. So these sorts of things eliminate some of the main reasons for going to the many-to-many model. Still, however, when we start thinking about extremely large number of threads, and as a community, this is something that comes up in the context of exascale computing, or when we are thinking about thread management in platforms that are really complex, that maybe have different kinds of processors, heterogeneity, etc., then it makes sense to start thinking again about user-level library support, about providing more custom policies for how threads are managed, how many threads are there going to be in the system, or similar issues. But for most practical purposes, the one-to-one model that's supported by the current Linux threading model is completely sufficient.